Hi, and welcome back. So we're still in Turbulence, which is still kind of this Chapter 8 undergrad, but also sort of the Panton Chapter 26 advanced portion. And so last time we spent a little bit of talk about the sort of the basics of turbulence and kind of finished on some fun visualizations. It really is truly, at least I find it one of the more exciting pieces. Again, that's why I ended up doing my PhD in that field and carried on a little bit as a professor doing some of that work. And so while last time I also sort of went into this challenge of modeling, I didn't get too deep in that. I do want to kind of come back today and both talk about, well, what can we model? What have we learned? There are some things that work pretty well with turbulence. It doesn't completely get us all the way there. But one of the things that we do know for wall-bounded turbulence, there are some similarities in like free jets and wakes and things like that. But for wall-bounded turbulence, sort of draw this here. We have a very good notion of what sort of what happens right at the wall and what happens in this thing called the log layer. And so this is actually going to be a log of something called y plus, and I'll define that here in a second. And then this is u plus. It's actually a different non-denominalization that you normally see. And effectively, this is u plus equals y plus. I'll get into that. And then there's a, I'm going to draw it in green, sort of these layers. I'll come back in orange and actually show what happens. So basically stick to that, and then you roll over, and then you have, you know, whatever your large scale phenomena is. Okay, so this is, you know, say 1, and this is like 10 and 100 and 1,000, and it depends on, effectively this is with increasing Reynolds number. So what's happening right at the wall is u plus is equal to y plus. Now the definition, so this is actually the definition of y plus. It's based on viscosity. And so, shear layer, let's see, y u tau over nu, and then u tau, u plus, this is basically u over u tau, and that ends up being u tau is the shear stress over density. So you can work for yourself and see that the units work out. Oh, that completely was off the screen. Okay, sorry. This is u plus is equal to u over u tau, and then u tau is the square root of the wall shear stress over the density. Okay, so it's basically normalization. You come up with a speed that's effectively related to the shear stress in the wall. So once you do that, this then follows through. So you can think about this as slow as a pipe. It works flow over a boundary layer, where you know with the shear stress. And so in a pipe, you know that shear stress is only going to happen because you know the pressure drop, and you can measure the pressure drop, and you know it. Or in a boundary layer, you can kind of measure it as well. So what ends up working really well, because we know these pieces, this is the mystery piece we don't have. So if it's a really complicated flow like around a car, these are things you don't know, and there's going to be pressure drag based on that in separation. But in terms of the viscous drag and things like that, at some point we can model this pretty darn well. And that's where some of the hope comes from in turbulence modeling, is if we can just kind of get most of this correct, then we can actually extrapolate through. So one of the things in a sort of turbulent pipe flow, one of the, if this is a pipe and you sort of have turbulent pipe flow, what it ends up looking like, this is sort of the average, is, it didn't do it very well. It ends up, I'll try to draw a little bit more. Basically, if this is turbulent pipe flow, there's supposed to be a gap there, compared to, say, pure laminar. Where laminar was that parabola, turbulent is sort of almost looks squished. The average is, again, remember the instantaneous is going to have all these twists and tumbles and eddies and vortices. But the average ends up looking like that. And so a lot of times the average in a sort of a turbulent pipe flow, you're going to do, this is little r over capital R, r being the actually radial coordinate and capital R being the radius of the pipe. And 1/7 is a decent approximation of what's actually happening here with this profile. And so that sort of works well for us. And then because experimentally pipes are fairly easy to handle in terms of, you're effectively just measuring pressure drop, thankfully a lot of this can roll back into the Bernoulli equation. And so, when I'm teaching undergrad fluid mechanics, some of this is why these sort of I'd say middle chapters as fluid mechanics starts getting like math heavy and complicated. It's actually in this sandwich of, it started off really easy. We were talking about just conservation of sort of perfect fluids. We were solving for forces, solving for buoyancy, and then insert all this complexity, and then you sort of come out of it, and then you basically go right back to Bernoulli. So some of this is why sort of the undergraduate fluid mind basically just ejects the part in the middle and says like, fluid mechanics got really hard there for a reason, and I don't know why. And then it just comes back to Bernoulli, and some of it is because of this. Because basically, you can come back now and say the pressure plus 1/2. Actually, I'll do this as rho g, so this is 1/2 v squared plus gz. Or actually just plus z. Yeah. So I've got rho g in the bottom at state 1 minus pressure over rho g. In fact, this is the g plus, we'll get it right, v squared over 2g plus z. So the difference in that we actually call head loss. So again, I've divided normal Bernoulli equation by density and gravity. And so this is units of inches, feet. So, if you're ever, I'm talking about like the pressure head is a couple feet of water, this is sort of what they're talking about. Okay. And this head loss usually then is modeled, this head loss H, the difference between, state 1, state 2. So you can think of this as an upstream of the pipe and downstream of the pipe. This head loss is normally then modeled as this friction coefficient, the length of the pipe divided by the diameter, and then v squared over 2g. Well, again, where v is going to represent sort of this, if you will, average velocity, or sort of peak velocity. If you start basically treating this as, no, I really want to treat this pipe as just there is a velocity that's happening. It's sort of uniform. So if the pipe is not growing in diameter, then the velocity is actually equal due to conservation of mass, because the density is not changing. So those would drop out. But this friction factor is, we can actually solve for it for laminar. So F laminar, again, because laminar flow is just a parabola, it's 64 over the Reynolds number. Okay, that's pretty easy. But otherwise, this friction factor is really a function of the Reynolds number in general, which is, you see it here with laminar flow, and the roughness. So usually the roughness is E, kind of the roughness of the pipe over the diameter of the pipe. And so what you do in practice is you say, I have a stainless steel pipe, or I have an aluminum pipe, or I have a whatever concrete pipe, and there are roughness estimates you can look up, or if for some reason you actually know the roughness of the system, you would look it up and you would go to this beautiful thing called the Moody diagram. And so there's your Reynolds number on the bottom. And what you do is you have a Reynolds number, and if it's laminar, you would just calculate it. They put laminar on here, but you could just calculate it. So you know your Reynolds number, and then you would look up, each one of these blue lines is the roughness, the relative roughness of a pipe. And so a very smooth pipe is sort of, you see all these lines kind of collapsing to this curve. And that's that smooth pipe sort of line. But each one of these roughnesses, you would pull the Reynolds number, you would go up to that roughness, and then you would read across to the friction factor. And so, again, that's where a lot of this can, at least in the case of a pipe flow, be really, really simplified down, not too bad to this case where it's just a friction factor, and I know the head loss. I know from sort of state 1 to state 2, what is this going to be, how much friction losses am I going to suffer in the pipe. And so this is super useful. If you end up going and taking your professional engineering exam, I did mine in sort of in fluid mechanics and thermofluids. There's just a lot of turning the crank on this problem. Like you have a pipe, a 12-inch Schedule 40 pipe, which is not actually 12 inches, so you have to look at the diameter, and then you come through and calculate a Reynolds number, and you sort of turn the crank on this a lot. So this is really, really useful. And then there's actually then also a list you'll see in every undergrad textbook, and you can Google it too. There are friction factors and or head losses for all sorts of things. And so there are losses for if I have sort of an entrance, like fluid flow coming into an entrance, or fluid flow coming out of into a tank, or in a pipe that has a sudden expansion, right? Because you actually get these eddies back here, or same sort of thing in a collapse. You actually get a thing called vena contracted. So there are actually all these estimates for what all of these geometries and what it does to, it just gives you an extra friction factor. And so I'd say thankfully a lot of this in pipe flow does actually have this what feels fairly empirical. And so, if you're just sort of sizing pipes, or even there are softwares out there that can do a kind of a complex flow of pipes and T's and splits and all that stuff. A lot of it is based just on this. That it's really not too bad. And part of the reason why I really, especially when I was teaching this in the university, really try to focus heavily on this turbulence appreciation was at least to show these videos of really complicated flows, was at least to get them to understand that, gosh golly, in most cases, you really actually can't predict any of this, which is why wind tunnels are super important, which is why CFD is super important. If you're trying to make a car better, or you're trying to make an airplane better, or sometimes if you're just trying to even make an airplane work, you have to know what is the drag and, at different speeds and different altitudes and different angles of attack and all that. To know that there's not really just this formula that you can kind of plug in. There are some estimates, but ultimately a lot of this stuff gets really too complicated to just sort of have this closed form solution. Because you literally get tricked in a pipe flow world. You basically get tricked into, hey, this is pretty simple. And so while this is powerful for pipes, it doesn't apply necessarily to a whole range of things, okay? And so that's actually how I'm going to finish sort of the next portion of this, is getting into external flows, where a lot of this really starts kind of going crazy. And some of this is then in chapter 9 of the fluid mechanics book. So I'll sort of draw it down here. So if you imagine an airfoil, okay? So I'll keep that in green. And let's just see all of the flows that are happening around what we think of as a fairly simple device, okay? So for instance, there's one streamline here that's actually going to come and stagnate. So we'll actually come back later and show we can actually solve for the fluid flow right around this, a little bit more of a graduate level problem. So it's very specific. So this streamline itself stagnates. Others slow down and then come around, okay? And then right here, this would be a laminar boundary layer where it's not yet fully tripped to turbulent. And then, at some point it's going to get bigger. There'll be a change in growth. This is then a turbulent boundary layer. Because it was over an airfoil, you actually have changes in pressure gradient this whole time. So the whole reason airfoils work is actually the fluid flow gets faster. So the flow is accelerating, which means that the pressure gets lower. And so you actually have pressure gradient at first, and then you have a reverse gradient, which is going to cause eventually this boundary layer to separate. And so all wakes, and we'll get into this again, it's going to get into more of detailed kind of graduate version of it. All of this is going to eventually have some sort of separation due to that sort of pressure building back up and the viscosity and all this stuff. It's really cool. And then on the suction side, usually this stays put. You can transition to turbulent. I'm not going to draw it here. There's some really fun visualizations we saw last time of this, and then it does sort of join the system in separation. And all of this can vary again with angle of attack, Reynolds number, and all that. Okay. And so in a generic boundary layer, so you can look at each one of these as, hey, this might be the application we're interested in, but in a generic boundary layer, again, I'll just sort of draw a wall. You can then think of different moments here where, again, this might be the laminar boundary layer, and this might be the turbulent boundary layer. And, the velocity profile, again, at the wall is 0. And then it's going to match sort of what we usually, the nomenclature is U infinity, like U sort of infinitely away from the wall. So sometimes it's called U0 for the free stream. And so a couple terms that it's worth introducing now, and we'll certainly come back to in the graduate level one. But the first one is displacement thickness. And so what it's basically saying is that you have some fluid flow mass flow loss here in the boundary layer. Right? If you look at initially, the whole thing was sort of U infinity, and then at some point here, it's back to U infinity, but I have a sort of a decrement. There is effectively a mass flow decrement. So if you go back to continuity, if I have a mass flow decrement in the x direction, it actually means there's a little bit of velocity vector up this way. It's true, it's small, but right, it's conservation of mass. But what we would then say is, okay, the density times that U infinity, and we will define this thing called the displacement thickness. The delta star is basically from 0 to infinity, and if you're calculating on a computer, you clearly wouldn't put infinity. It's to basically say get outside the boundary layer before you stop this calculation. It is, what is that decrement? Okay, In one way, it's effectively saying, I'll try and draw this in red if it shows up here. It's effectively saying, if I did have u infinity, and then magically my velocity went to 0, yeah, that didn't show up at all. Okay. It's basically saying I had u infinity, and then it magically went to 0. What is that del star? What is that, the height of that gap? If my boundary layer, instead of being sort of gently curved and going all the way up to infinity, what if it was a step function? That step function width is the displacement thickness, okay? And then similarly, you're going to, they define a momentum thickness and use theta. Oops. Use theta. And then this is integral, again, from infinity. And then it's basically, again, what is that decrement? Now, usually you divide by rho and the u's on both sides for your normal calculation, but I'll just kind of leave it there for now. Same sort of thing. This is sort of a momentum thickness deficit. So again, I'll come over here to this boundary layer. So again, if the velocity profile actually went from u infinity and then did a step function to 0, and I wanted to say what is actually the equivalent momentum of this, then this one would be theta, this distance here. Okay. So we'll come back a little bit more in sort of the graduate version, where we actually will make use of these. And this is introduced a bit in the undergraduate, but a lot of times these variables are what we'll then plot. So it's just like coming over here and plotting something versus y plus or u plus. It's for us to try to understand as we have this application here of an airfoil that we're trying to, we might be talking about what is the displacement thickness, or maybe even the community I was in, gas turbine engine research for a little while. Like these are things that you would plot and talk about, so that you can talk about you can start using like theta as a Reynolds number, right? So remember, a Reynolds number is rho times some sort of velocity. So maybe you take u infinity times a length scale divided by nu. And so there's actually a definition of Re theta, which is based on the theta. And so this is a very useful thing when you start talking about really, again, real applications, which is where this comes back to, which is why, as much as I love that Moody diagram, it will give undergraduates the wrong taste in terms of turbulence and fluid mechanics is a known thing. And it's like, oh, gosh, we were just trying to leave you with the one tool that we actually have. And for the rest of this, it's still really, really hard. Okay. And then what I'm going to sort of finish here on the right is within these boundary layers, we can actually come back. And this is very much a graduate level solution. So this is why I'm sort of including kind of Panton here. That's not in chapter 26. It's a little bit earlier. And you actually do see it in the undergraduate text. But again, it sort of just gets sort of stomped over. And so if you define a variable called eta, and that variable is going to be the distance away from the boundary layer, and then u, and then over kinematic viscosity times distance, x being the distance along the direction here. And then you go back to a 2D flow where you have a stream function. So the x velocity being the gradient of the stream function in the y direction, y velocity being negative, the gradient of the stream function in the x direction. And you come back to conservation of momentum, sort of steady state. So I'll write u du dx plus v du dy. And we'll do this in the case of a zero pressure gradient boundary layer. So there's no pressure term here. And then you just have, so nu, just sort of a reminder where I draw it here. Nu is actually just viscosity over density. So you still hear I've gotten rid of the density on the momentum turn, and so I'm using nu, kinematic viscosity. Okay? And then this would be the second derivative of u with respect to x squared plus the second derivative of u with respect to y squared. Okay. Before I write the y momentum equation, first couple things, the velocity of this, the change rate of the x velocity in the x direction is small. It is changing, but it's small. And so the second derivative of it basically we'll say is, no, that's tiny. So we're going to ignore it. Okay? And then what you do is you would come in and replace all of this with now the stream function definitions. And so this is now d psi dy, du dx. So this is the second derivative of psi with respect to x and then y. And then velocity, so actually it picks up a negative, d psi dx, and then second derivative of psi, and it's u, so it's y, so with respect to y squared is equal to nu, and then this is the third derivative, and then it's of psi, and u is y, so that's actually with respect to y cubed. Okay, and so not to get follow along the book. Along the last step I'm going to say here is just to recognize that u, which is d psi dy, is actually, we'll chain rule it, so it's d psi d eta, this new variable I've defined, d eta dy. Okay? And so if you do that math, right, then you'll end up seeing this is basically the square root of nu x u, and then we'll call f prime, and then u over nu x, which is then just u f prime. Okay. And so the final version where this gets you, after you sort of combine and pull it in, so go read this in the book, what you end up with is a third order differential equation, 2f triple prime plus f double prime is equal to 0, and your boundary conditions are at eta equals 0, you have f and f prime is equal to 0, and at eta equals infinity, you have that the first derivative of f is equal to 1. Okay, so this can be solved. Okay, and it's going to come back to if it's laminar, then we can actually have the boundary layer can actually be solved. So 5x over square root of Reynolds based on x. And then where this lets you then completely come back to the coefficient of friction is 0.664 over the square root of Reynolds based on x. And Reynolds based on x, come back here. That is, again, Reynolds number is just the density velocity times a unit of length. And so Rex is actually then the x distance along the boundary layer divided by viscosity. So this is then laminar, and then you can look up in the book what it is for turbulence. Actually, you know, I didn't write it down here, but I know what I do remember. This is 1/5. I think it's like 0.332 or a small number. I won't write it here. Go read it in your book. I didn't write it down in my notes. And so this actually a little bit gives us some hope. Kind of back to the Moody diagram on turbulent pipe flow. This gives us some amount of hope on boundary layers, at least with zero pressure gradients. And so, you know, if you're doing in undergraduate, like sort of there in chapter 9, you're going to see a whole bunch of problems, which is like, you have a boundary layer, what is the friction? And so some of that is really then just kind of a two-step problem. Well, three-step. Do I have a pressure gradient? Usually in the undergraduate versions, no. And so you would then just say, okay, am I laminar or turbulent, or some mixture, right, of both? And so that will then actually, once you have the friction coefficient, that lets you then solve for the shear stress, but then solves immediately for the drag. So I'll just finish with, again, turbulence is one, it's beautiful, it's chaotic, it's all of these different motions. It's still really, really, really hard. And so as engineers who were trying to build real things that go through real fluids, whether it's cars, submarines, boats, aircraft, all of those things are real problems which need real, no kidding, both models, which are really hard, and then wind tunnels and computational fluids. And we talked a little bit about both. Why? Because ultimately, knowing the drag around a surface, knowing the boundary layer can be challenging. In certain cases, we can actually estimate it well. In other cases, we can't do any of this. Right? And so let me finish back with this airfoil picture. So the laminar boundary layer here, we can estimate with this. Again, it's wrong because I do have a pressure gradient. You have to pay attention to any pressure corrections. Then I have a turbulent boundary layer, which I could estimate with the second number. But then I have a separation, and that I can't estimate. So the result is this is really, really hard, but it's also beautiful. And that's why throughout this sort of book club series, as you're reading, that's why I'm grabbing all 4 of these books, is because you can go in and you can read little bits and pieces of each section to where this doesn't necessarily scare you because your math has been upped. You can follow through, and we'll actually come back into in the graduate version, there's many solutions like this that involve a similarity variable that sort of turns all of this XY conservation momentum into a differential equation that we can solve. By the way, you solve this numerically on a computer, and they could do that even back in the day. So it's a beautiful subject. It's hard, and so we'll see you next time on Book Club. Especially go through and read these books. Make sure you're solving the problems. That's the whole point of this book club. I'm only giving you the high level here to hit the wave tops so that you, dear reader, are doing the rest of the work in the book. So we'll see you next time.